So let's show an example of opening and closing in MATLAB. So we'll use the same functions to create a structuring element. This time let me create a disk of radius r. I'll use 3. The n parameter is optional, but it is the number of line segments that's used to approximate the boundary. If you put in 0, it doesn't use any approximation. So this is a structuring element approximation of a disk with radius 3. So I'll go ahead and read that same image again. And apply an opening. So what we've done here is opened this image, and the parts that remain are the same size, but all of the parts that were smaller than that disk have been eliminated. It looks like I have some parts of this disk that just happen to be slightly smaller than my structuring element. Okay, let's try the closing. Okay, so here we have, again, we have the objects that are the same size, but we've filled in any gaps. So for example, places where I had a small gap between two regions are now filled in like that. All right, so one final algorithm we'll look at today is connected component labeling. So connected component labeling is very useful. It relies on this notion of connectedness, and in 2 dimensions we can have 4 connectedness as shown here, or 8 connectedness shown here. So this basically says this pixel has these neighbors, these 4 neighbors, or I can consider it to have these 8 neighbors. So 2 pixels are connected in some set S if there is a path between them consisting entirely of pixels in S. So if I had 2 regions like this, obviously those are not, those 2 pixels are not connected because I would have to go outside the region to these points between them would not be part of that 8 or 4 connectedness. But if S was somehow closed like that, and I went from one path to another, then this set, these 2 pixels are connected. So my set is a connected component. Sometimes we call it a blob if there is a path between every pair of pixels in the set. So labeling is the process of assigning a label number to every pixel in a connected component. So let's say I had 2 connected components, S and T. And so basically these are points that have 1s and outside is 0s. So the process of labeling would be, if I can draw the same shape here, to assign the same value, let's say label 2, to every point within S, and then another label, let's say label 3, to every point in this region T. Okay. So let's do an example on a simple image like this. So if I have a 4 connected if I consider these the property of 4 connectedness, then these pixels are certainly 4 connected. I could use the label 1, for example, for those. These guys are 4 connected. I could use the label 2. these two would be another component, let's say label 3, and this one would be its own component, let's say label 4. If, however, I use 8 connectedness, then these two regions are connected because I have the property of 8 connectedness there. So I would have to use the same label, let's say a 1, for all of the pixels in that region. And I'd still get 2 other regions here and here. There's a fast algorithm to do this labeling on a binary image. As we'll see here, it's 2 passes through the image. The first pass assigns temporary labels and records equivalences between labels. And a second pass replaces the labels, the temporary labels, with the equivalence labels. So on the next page, we'll say that B is the input binary image, L is the output image of labels. So algorithm starts like this. We have our binary image B. We go through it in scanline order like this. And we test if a point is equal to a 1. So if we find a 1, then we go through the rest of the processing. Otherwise, we set 0 for the label image. Okay, so if we have a 1 there, then we need to check a couple of conditions. So the first condition we check to see is, are we at a point where the previous row is also a 1, but the previous column is a 0, like that. So I could say that by if L of R minus 1 C equals 0, equals, let's first consider the case where they're both zeros. Okay, so that's a 0, and L of R, let's see, I'm sorry, this should be a B, not an L. So if B, the binary image, above me and to the left of me is also 0, then I basically have discovered a new region. So I'm going to increment my label counter and assign that to L. So another situation would be if I'm at a 1, my previous point is also a 1, my left point is a 0. So in other words, B of R minus 1 C is a 1, and B of R C minus 1 is a 0. In that case, I want to assign the label at this point to be the label of the point above, because that guy has already been assigned. Another case would be if the left point has been assigned but not the point above. So that would be R C minus 1 and R minus 1 C, in which case my label at that point is just the label of the neighbor to the left. So finally is the case, the difficult case, where I'm at a 1, but the point above and the point left are both 1s. In this case, I have to pick one or the other of the labels. And unfortunately, it's possible that the two label numbers could be different. In which case, I'll just pick one arbitrarily. Let's say I pick the one to the above me. So I'll call that, say, L1. And I'll record equivalence of of L2 here as well. So I'll record the fact that L1 and L2 are equivalent.